All right, so we are recording, and because now I finally remembered. My bad. Hello. Anyway, um, let's see. So where were we? Um, so Mengru, I just don't know how to show their ideals. Okay, so Mengru 1374. Um, oh, um, right. So in 1374, let's see if we can scale down a little here. So on 1374, here we go. 1374 to show to show that P and Q are ideals. That's what Mengru. That's what you're asking about. Mengru. That's what you're worried about. Oh, prime ideals. Um, oh, so to show that they're ideals. Okay, the ideals are prime. One method is to show their norms are prime. Prime because an ideal with a norm that is prime can't factor because its norm can't factor. Does that make sense? Yeah, okay, so that should be okay. So any other questions about the homework? So how was that? Was that as hard as last time, or a little more manageable, or sort of, or even worse than before? Any opinions? Same. Equally hard. Okay. All right. Well, I think at least the next one, you sort of get a payoff in that in 13.8 you get to compute some stuff, and it's very satisfying when you like get an answer, and and well, I mean, you can check it online, I guess, but it's sort of satisfying to see that it actually works. Uh, okay, yeah. So this is pretty challenging, but after this, I think we're gonna sort of ease back down just a bit and do some more sort of slightly more human scaled stuff. So all right, so is everybody ready for chapter 15? Are there any are there any last questions before we go? You can just say ready in the chat, or last question, or put in a last question. Oh, hi, colors. There you are. Okay, everybody's ready. Let's go. Oh, and this system. So I actually I spent $70 and I bought like an actual piece of software. God forbid you should actually pay money for software. But this works better, right? This is better than the sort of annotation I was trying to fumble with last week, and well, I didn't actually curse, but I thought about it. So this is better, right? Good, Trent. That's the right answer so far. Let's see what screws up next. Okay, so let's talk about extension fields. So now for yes, and yeah, what are we doing now? We are now doing. Uh, whoa, that was not what I wanted to do. What the heck was that? Trent, you are correct. That was spoken too soon. Okay, what was that? Uh, nope, that's not okay. I'm not going to do that 3 times anyway. So that does that every time. All right. Anyway, the point is, and now for something completely different. By the way, do you guys all watch Monty Python? Are you familiar with that oeuvre? Yeah. So there's your, this is a Monty Python segue. So this is something, yes, now for something completely different. Okay, here we go. Okay, so definition. So the sort of problem that we're looking at starting in chapter 15 is about the following situation. So if K is a field that contains a subfield F, I guess you'd make this more complicated, but you could say like let F be a field and let K be a larger field that contains F. Okay, same thing. K is a field containing a subfield F. We write K over F to refer to that situation, and say that K is a field extension of F or an extension field. So far, so good. We'll have some examples in a minute, I think at the bottom of the slide. There they are. So definition. So one thing to notice is that if K is an extension field of F, then K is an F vector space because because let me sort of say, I guess I should say why, because why not? You can add elements of K. You can F multiply. You can scalar multiply them, and all the usual and all the rules of being a subring tell you that all the usual things that you can do with vectors will work with K. Yeah. So one of the odd little things, actually this took me a long time to what is that? Oh my goodness. I see what happened there. All right. Sorry, I got distracted by that. I see an error down below, but okay, my bad. All right. So yeah, one of the things that took me a long time to get used to is the idea that when you look at a field extension K over F, one really important and useful idea is to think of it as K as a vector space over F. So we define, and keeping that in mind, we define the degree K colon F of K over F to be the dimension of K as an F vector space, and to say that K over F, the extension K is finite, means exactly that the degree K colon F is finite. So this is all clear except for the typo that I made down here. This is all really clear in terms of considering examples. So let me give you some examples. So for example, the complex numbers are an extension of the real numbers of degree 2. And why is that? It's because if you look at the complex numbers 1 and I, that's a basis for the complex numbers over the reals, and a somewhat fancier but actually more typical extension that we'll look at. If you look at Q bracket root 2, that's actually a field. It's not obvious, but it's true for reasons that we'll examine in a minute. So Q bracket root 2 over Q is also an extension of degree 2, and that's because I don't know. Well, somebody want to take a guess as to what a basis for Q adjoin root 2 over Q will be? Thank you, Trent. Yeah, so 1 and square root of 2 is a basis. Let me remind you that that Q adjoin root 2 is the set of all A plus B. Oops. Interesting. So sometimes I get a little pen fail when it gets in that area there. B root 2, where A and B are rational. Okay. Yeah. So this indicates spanning over here, and actually you may remember we actually talked about a result earlier a couple chapters back where that showed that 1 and root 2 are linearly independent because x squared minus 2 is irreducible. Yes, and so this I messed up. Let me see if we can get a different color here, just for just for fun, let's make it bright lime green. So what's supposed to be over here is supposed to be F3 bracket X. And here's a if you're wondering where the typo came from, how did I get it equals 3? What happened was that I, instead of having underscore, I hit equals. That's the name of that tune there. Oh well. Anyway, the point is F3 bracket X mod X squared plus 1 is a field because X squared plus 1 is irreducible over F3, as you know, because X squared plus 1 has no roots in F3. Just plug in 0, 1, and -1. None of them give you 0 when you add 1. It turns out that the order of F is 9. There's 9 elements, and which means that that the degree, because 9 is 3 squared, 2, because 9 is 3 squared, that means that the degree of F over the field F3 is actually 2. And in fact, all finite fields can be constructed in this way. So one of the things that we'll sort of it's maybe not sort of completely directly in the line of our main thrust of sort of of our argument, but one thing that will happen is that that we will sort of stop for a bit and develop the theory of finite fields, which is really pretty cool. It's a very nice theory. How many of you saw the theory of finite fields? I've forgotten. I think I asked this before, but can you say in the chat who's seen the theory of finite fields? Excuse me. All right. So yeah, I think and the 3 of you who said yes, you saw that in 128b. Okay. Yeah. So I think a bit is probably about right, and we'll see a bit of it again in about a couple weeks, at least according to plan. Of course, these days, who knows? All plans are written in sand. Wait, any questions so far about field extensions or degree? Are we good to move on? Say yes. Can everyone hear my daughters talking in Chinese upstairs? We're trying hard to preserve normality. How's everybody doing? Everybody getting by okay? Yeah. It's true. What do you say? Anybody come up with a good song for our DJ period to begin class? Anyway, just think about it. I can only bring up the chat. So by the way, for those of you who got to the chat earlier, I was playing the cha-cha slide because I think the idea is to sort of just pick a song that has some meaning to you, however, or makes you feel comfortable or puts you in a good mood. And I picked the cha-cha slide because that's actually the sort of morning assembly music for my daughter's elementary school. They all sort of get, well, in happier times, they would get together and do the cha-cha slide at the start of the day. Anyway, let me go turn back from the cha-cha slide to extensions. Okay, so the main topic, what we're doing, sort of the main thrust of what we're doing today is we're going to be talking about how to extend the field by single elements. So sort of technically, what's going to happen, this is sort of what's going to happen eventually is that this is going to be our main technical tool. Our main technical tool. So yeah, so what we're gonna do is so when we actually do sit down and do calculations, because God help us, we're actually gonna do some calculations and like get some stuff going on there. Um, our main technical tool will be extension by a single element, and that ends up sort of when you do calculations in what's going to be Galois theory by the end of chapter 16. Uh, generally, you try to do extensions by a single element. Okay, so we're to spend a little time now and to get into the details of how extending a field by one element will work. Okay, so of course we have to start with definitions. So let K be an extension field of F, and let alpha be an element of K of the extension. Though I guess, if alpha is an element of the extension, it could also be an element of F. Just keep that in mind. That's sort of a trivial case in all these definitions. To say that alpha is algebraic over F means that there exists some f of x. You can make it a monic one if you want, because you have field coefficients. You just divide out by the leading coefficient. So there exists some monic f of x in big F bracket x, such that f of alpha is 0. That is, so to say that alpha is algebraic means that it is a root of some polynomial coefficients in capital F. And if no such f exists, then we say that alpha is transcendental. Nice word. All right. So for example, the square root of 2 is algebraic over the rationals, and pi is transcendental over the rationals. Just to see that everybody's sort of tracking here. Is anyone, maybe someone who hasn't chatted about this yet, maybe someone who has not seen this material before, somebody want to say, or maybe kind of remind us what the f of x here is that makes the square root of 2 algebraic? Just say in the chat. All right, thank you, Apurva. This is f of x is x squared minus 2 equals x squared minus 2 is the well, I was gonna say it's one of the polynomials that makes a square root of 2 algebraic, but in some sense, as we'll see in a minute, it's basically it's the defining polynomial that makes root 2 algebraic. And now pi is transcendental over the rationals. That's actually pretty hard to prove. I don't know a proof off the top of my head. It's a sort of specialized it's a specialized topic of number theory. Actually, let me see if I have this down here. No, okay. So anybody? I looked this up on Wikipedia last night, so I think I still think it's true. Yeah, you want to hear? Does everybody want to hear an open problem? It's been open for forever, I guess. As long as the definition has been around. So here's an open problem. Open problem. Is pi algebraic over the suspense over the rationals adjoin E. So right, so that sounds ridiculous, right? That's a completely ridiculous open problem. Is there some polynomial? When I say E here, E is like 2.1, 2.718281828. So the open problem is there some polynomial in E that when you plug pi into it, you get some polynomial, the coefficients in rational numbers and E, some combination of rational numbers and E, that when you plug pi into it, you get 0. That's like the most ridiculous possible open problem. Like, how could that possibly be true? And yet, no one's been able to prove it. So I don't know. Go prove this, and that'd be a good master's thesis. No, I don't know. You prove this and make yourself wicked famous. But it's some measure of how difficult it is to deal with transcendentals that we have no idea that we mean, not we meaning you and me, but we meaning the human race have no idea whether this is true. Anyway, I thought that was cool. That's a total digression, but but it's an interesting one, huh? Anyway, getting back to our main topic. So here's an alternate description of being algebraic. So consider let phi be the substitution map that from f bracket x to k that sends f of x to f of alpha. So if we rephrase the previous definition, right? The previous definition that algebraic means that there's some f that when you plug in alpha you get 0. That's exactly the saying that alpha is transcendental exactly when the kernel of phi is 0, exactly when phi is injective. Otherwise, the kernel of phi is going to be generated by some monic polynomial g of x, because somebody else want to chime in? So how do I know that the kernel of phi is generated by some polynomial? Someone else want to chime in on that? I'll start. Ooh, this is important. So is everybody actually puzzled here, or because then we should go back and make a point of reviewing this at least briefly, or is there somebody out there who wants to say how we know this g of x exists, but it's just being shy? Okay, right. All right. So can everybody turn on their mics? Let's chat about this for a second. So can anybody willing to be recorded turn on their mic?
Hello.
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 Hey.
Hello.
Hello. Okay, so let's review this. This is important. This is an important point because this will come up repeatedly. So how's this go? So the point is, remember, kernels are ideals. Oh goodness. I hope you're feeling okay. Yeah. So kernels are ideals, and what do we know about the ideals of f bracket x?
They're principal?
They're principal. That's exactly right. So the reason that the kernel of phi is generated by some polynomial g of x is because f of x, f bracket x, is a principal ideal domain. And yeah, so that will. So yeah. God forbid we should use all that stuff we did in chapter 11, but there it is. Right. And right. So it all goes back to. And you can turn off your mics now if you want, or leave them on. Zoom seems like not to be failing. I'm actually pretty impressed. Famous last words. Trent, how did you put it? So far, but well, here we are. Okay, so not failing yet. That's right, Trent. Anyway, so so the point is, kernels are ideals, and ideals of f bracket x, where f is a field, are principal. And so there's always going to be some generator. That's, that comes back again and again. Okay. Anyway, so the point is, so we know that that this ideal has some monic generator, and that monic generator has four equivalent descriptions. It's the monic polynomial of lowest degree, that when you plug in alpha you get 0. It's also the unique irreducible polynomial, such that such that G of alpha is 0. Let's see what else. That means, so being irreducible, it has to be the ideal that it generates. It has to be maximal, and it's a GCD. It's a GCD. This is just sort of saying here. Let's see. This is saying that this is a GC. The GCD, little g, is a GCD of everything in the kernel of phi. Yeah, and so the degree of alpha is defined to be the degree of G of the element alpha. So now we have two. I guess I should point out here. Now we have two definitions of the word degree. A word that's almost abused almost as much as order, unfortunately. So we have the degree of a field extension, and now we have the degree of an element. Fortunately, in a minute we'll see they sort of mean the same thing here, but you know, I did want to point out that we have, at least at this point, two ostensibly different meanings of those two words. So how are we doing so far with this idea of the let's see, what is the main idea here? We have when we have an algebraic we have an algebraic element over of a field extension, then it has a sort of monic irreducible generator g of x. For that generates the ideal of all things that when you plug in alpha you get 0. Yeah, it generates the ideal of all polynomials in capital F that have alpha as a root. Okay, so are there any questions so far? Whew. So are we okay to move on for now? Okay. Let's move on. Okay, so here's some. Oh, I have absolutely. Let me actually sort of do one. I was gonna do a little something here, and I was like, there's no blank space, but look, there actually is a little blank space. So I'm going to prove this below. Okay, so because this is sort of a sort of. So this is a little bit of an intrusion from above. I'm going to prove star. So star says, why is it that if you have a non-zero monic polynomial of lowest degree, such that g of x, g of alpha equals 0, that polynomial has to be irreducible? And I think this is, I'm not sure this is an argument that we've seen before. So here's why that is. If g of x equals f of x times h of x, then it must be the case that f of alpha times h of alpha equals g of alpha equals 0. But because k, so everything here is happening, everything here in this fraction, everything here in f, h, and g is happening in big K, because big K is a field and therefore an integral domain. Either f of alpha equals 0 or h of alpha equals 0. So one of them, so if one has a strictly smaller degree, we get a contradiction. Anyway, so again, that's just a proof of this, of one part of this four-part equivalence, that having a polynomial of lowest degree, any polynomial of lowest degree has to be irreducible, and that's because, well, if you could reduce it, then one of the smaller pieces would also be something that has alpha as a root. So I guess that sort of always happens. Anyway, just so you know. Okay, so let's see. So if we're gonna talk about some examples, then first we're going to talk about some notation. So there's a subtle distinction. Well, there's a subtle distinction which we will very quickly erase, for better or worse. Oops, sorry about that. This is one. So this is like my part-time job now. Like I'm a DJ. Interesting. So you to not tapping the mic. Okay. So there's a subtle distinction which we shall sort of immediately erase, because oops, there we go. So F parens alpha is the smallest subfield of K containing F and alpha, but in contrast, F bracket A is the smallest subring of K containing F and alpha. So so F bracket A is by definition closed. F bracket alpha is by definition closed under multiplication, addition, and subtraction. But F of alpha is also closed on F parens alpha is also closed under division, undertaking reciprocals of non-zero elements. So in principle, that's the distinction between F bracket alpha and F of alpha. And there's a similar thing for sort of adding more than one element. Yeah, we'll get to that. Oh yeah, sorry, I just want to introduce that notation just in order to talk about like what this is. This is, yeah. Why do we have to introduce that notation? It's because exactly because of this. This is the smallest field containing Q and square root of 2. Yeah, that's the only reason I wanted to introduce the notation. Oh, I mean, I want to just introduce it for later. But that's the immediate need for it. All right, so for just to give two examples about about how different the irreducible polynomial for an element can be over different fields. If you look at the irreducible polynomial for the sixth root 2 over the rationals, it's x to the 6 minus 2, similar to examples we saw before. But if you expand the base field to q root 2, then the irreducible polynomial for the sixth root of 2 is over q adjoin root 2 is x cubed minus root 2. And it's sort of instructive to see this sort of phenomenon that happens when you sort of, if you expand the base field, what happens? Yeah, what happens when you expand the base field? When you expand the base field, what happens is that the polynomial, which used to be irreducible under the smaller base field, x to the 6 minus 2, can suddenly factor, which, as those of you who are teaching, well, I guess you wouldn't actually assign this in college algebra, but in principle, this is college algebra, sort of, kind of. If you may notice that x to the 6 minus 2 factors as x cubed minus root 2 times x cubed plus root 2, and so yeah, I guess that's kind of like this argument that we had over here, that if you can factor the thing that you thought might be the minimal polynomial, well, then it's not the minimal polynomial because one of its factors has to be a sort of smaller minimal polynomial. Must be the actual minimal polynomial. All right. Geez, I don't know. It was late. It was late when I prepared this slide. I can't exactly remember why I did this, but yeah, I think it'll come in. I think it illustrates something at least. It at least illustrates that the irreducible polynomial for a given element, an algebraic element, depends on how big you make the starting field f. Yeah, that will come in. That will show up later. So, any questions about that so far? Everybody okay out there? More or less. Okay. All right. So let's see, how many slides do we have out of this? Well, I guess we get as far as we get. It's no big deal. So the idea is that the next result is that if alpha is an element of a field extension K over F, and alpha is algebraic over F, and F is the irreducible polynomial for alpha over F, then we have an isomorphism from f bracket x to mod f to f bracket a, and f bracket alpha, and f bracket alpha is actually a field, which means, in fact, that f bracket alpha is equal to f parens alpha. And something similar works for adjoining multiple elements. So having very carefully introduced that distinction between bracket alpha and parens alpha, adjoint alpha, we now wipe that out because we will mostly deal with algebraic elements, and for algebraic elements that there actually is no distinction. Let's see. So look, I said proof. That must mean I'm supposed to prove something. Oh boy, that I hope I can actually do this. And this maybe made more sense when this seemed easier when I was less tired last night. Okay, so there's two parts to this. There's sort of two statements, and the third statement will follow from that. The first statement is that we have an isomorphism. This is, the fact, remember, f of x, we just saw a couple of slides back that f of x, the sort of irreducible polynomial, generates the kernel of substitution. So because f of x generates the kernel, the star holds by the first isomorphism theorem. What? We never use that thing, but okay, yes. There we go. This is like one of the few times we actually use the first isomorphism theorem. So that's true. And for double star, why is f bracket alpha a field? F bracket alpha all right. Somebody want to take a stab as to why f bracket alpha is a field? This is something you can type in the chat window, and no one will see. Well, and no one will see on the recording. I mean, I guess I don't know if you felt really private. You could just type it to me. Very good. Thank you, Aruba. Because f of x is irreducible. So remember we saw sort of in general that when you take a ring of polynomials with field coefficients and you kill an irreducible, you get a field. And to fill in one detail of that, if f of x is irreducible, that's the same thing as saying that because f bracket x, capital F bracket x, is a PID. F of x being irreducible implies that the ideal containing f of x is maximal, which implies that big F bracket x mod little f is a field. So again, we actually go back and use all that stuff, huh? Almost as if there was some plan to the whole course. Well, okay, maybe it's not. I'm not saying it's my plan, but there is a plan. Okay, so that's why, so that's why, having carefully introduced this distinction between f bracket alpha and f adjoin alpha, we're just going to ignore it most of the time because the alphas that we use are almost all going to be algebraic. All right, and there's an old result that I want to recall. I don't want to reprove it, but I think it's sort of worth remembering that if the degree of f is n, then the elements 1 alpha through alpha to the n minus 1 are those elements form a basis for f of alpha as an f vector space. All right, so let me say, let's just do one example of this. Somebody want to give me an irreducible f of x? Just type something in the window or turn on your mic and say something.
How about x squared plus 1? Does that work?
Yeah, that's a good one. It's a classic. X squared plus 1, which means that that our alpha is I. That's going to be our or actually, just for a little variety, I'll make it minus I. Where's my eraser? Dang it, I had an eraser here. Where'd it go? Oh, there it is. It's blue. There we go. Try this. Is that really going to work? Oh, it worked. No, it didn't. Okay. I'm still working on the controls for this. All right. So alpha is I. Oh, I just said it. All right. Sorry. I got so excited about this silly program. All right. Minus I. Because it works just as well. So F is irreducible. So 1 and minus I is a basis for F is irreducible and degree 2. So so the set containing 1 and minus I is a basis for F adjoin alpha. I mean, I think, and that was actually, or sort of in general, 1 comma alpha. And you may remember, this is actually something we saw in some other context, but just as a reminder, that's always the way you sort of compute. That's always the way that you compute when you take. Oops. Apurva, did you ask again? Oh no, that was 5 minutes ago. You asked because f of x is irreducible. All right, so yeah, that's always the way you compute when you take f bracket x and kill a polynomial. So I hope everybody has some memory of that. If not, you can go back and look at it. Okay. So are there any other questions so far before we go on to our remaining topic of field isomorphisms and automorphisms? Okay. All right, so let's talk about how to construct field isomorphisms and automorphisms. All right, so again, as always, we start with the definition. So an F isomorphism, K over F to K prime over F, where K, those are both field extensions of F, oops, is an isomorphism from K to K prime. You can see you can see I did this in a hurry. So an F isomorphism from K over F to K prime over F is an isomorphism from K to K. A field is a field. Hang on. Let's try this. Sorry, when the chat window is in the way, which you can't see, I have trouble writing. So an F isomorphism, the field isomorphism from K to K prime, that is the identity on F. To say that K over F and K prime over F are isomorphic extensions means there exists an F isomorphism K over F to K prime over F. All right, so now, did I revert to L? No, that's fine. So suppose alpha is an element of K over F, and beta is an element of some other field extension L over F, and both alpha and beta both. Did everybody hear my New England accent come out there? I said beta. Both alpha and beta are algebraic. So in that case, there exists an F isomorphism, F from F alpha between F alpha and F of beta, F adjoin alpha and F adjoin beta, sending alpha to beta exactly when their irreducible polynomials are equal. Okay, so proof is maybe actually sort of a little bit over fancy. So the idea is that so let F alpha and F beta be the irreducible polynomials of alpha and beta respectively. See, there's my New England accent again, beta, alpha and beta respectively. There we go. So what happens is we just saw that F bracket X mod F alpha is isomorphic to capital F of alpha, with X getting mapped to alpha. And we also just saw that capital F of X mod F of beta is isomorphic to F of beta. I guess the arrow should go both ways because it's an isomorphism. Maybe not so much proof as this is why this is true. And what happens is that, let's see if we can get a different color here. These are isomorphic if and only if F sub alpha equals F sub beta. No. Let's see if I can move that. That is not the, is this the thing I want? Nope. There. Oh my God, that worked. There we go. Okay. Yeah, so the thing that happens is that these two things are isomorphic exactly when those two polynomials are equal. Right. I mean, that's the idea of what happens. I mean, I'm sort of leaving out a little detail that I'll get back to later. But at least it should be. I think it should be relatively clear that if the two polynomials are equal, then these two fields are isomorphic. And the converse is maybe not so clear, but I'll come back to that later. But any questions so far? All right. Oh, actually, I should type the upshot of this. Let me see if we can get a different color for this. Is there a good color? Oh yeah, look, there's different colors here. I'll have, let me try dark. Oh, let me try orange. The upshot. Oh, actually, the usual application of this, if two algebraic elements have the same irreducible polynomial, there exists an isomorphism in field extensions. So the way in which we will use this most of the time is that when you have two we want to prove that there is an that there exists a certain isomorphism of field extensions, and what we'll usually do is that we will we'll say, like, well, the reason is because these two things have the same irreducible polynomial. Okay, so now here's some examples. Yeah. Okay. So and we're actually going to use exactly that application, that if that two algebraic elements have right. So so here's an example. I'll do the first one. So here's the first one. Let me go back to blue. I like that blue. So for example, when you look at oh, sorry, let me go back to pen here. This is sort of like your alpha, and this is your beta. So so let me just sort of type out the explanation of what's happening here. So there exists an isomorphism of field extensions. Oops. I want to make this very long. Extensions from q of square root of 2 to q of minus the square root of 2, sending square root of 2 to minus the square root of 2, precisely because both of those elements have the same irreducible polynomial, x squared minus 1. So so there are a couple. So one of the things that at some point we're going to have to do a lot of is we're going to have to we're going to have to show that there is a field, there is an isomorphism of the field q adjoint square root of 2 to the field q adjoint minus the square root of 2 that sends the square root of 2 to minus the square root of 2, and we're going to have to do that sort of thing all the time. Like, why is that? How do we show that there is an automorphism, an isomorphism from the first field to the second, sending the first element, sending alpha to beta? And the answer is always going to be like, well, they have the same irreducible polynomial, so there must be a field isomorphism between the two extensions. And in fact, usually what we'll do is it will actually use that. We'll actually apply this in exactly this situation. What really happens here is that that the field q adjoin root 2 and the field q adjoin minus root 2 are actually the same field. They're actually the same field. So they're so this is actually a field automorphism. It doesn't seem to want to expand here. Let me try to. Excuse me. Whoa. There we go. Yeah, it's the same. It's so those two things are actually the same field. So there's a field automorphism. That's actually a field automorphism. Okay, so so is everybody good so far? Okay, so in a very similar way, I guess these are not the same field, so it's not really. So here, I guess I better use a pen. Q adjoin root 4 over the fourth root of 2 is not equal to Q adjoin I, the fourth root of 2, because, for example, the first field is real, entirely composed of real numbers, and the second isn't, but they are isomorphic. Actually, I want to be, let me be a little bit more careful here. It's not just that they're isomorphic, it's that they're, but the fields are actually Q isomorphic fields. But those field extensions are Q isomorphic. There is a field isomorphism between the first. There's an isomorphism between the first field and the second field that fixes the rationals and sends root 4 of 2 to I root 4 of 2. So sort of these two elements are algebraically indistinguishable over the rationals. On the other hand, if you look at the elements root 4, the fourth root of 2, and I times the fourth root of 2 over Q adjoin root 2, those are not isomorphic field extensions because they're isomorphic fields, as we just saw. Because they do not have the same irreducible polynomial over Q adjoin root 2. I sort of had to do this, but actually maybe this is a little tricky. So over here, so in the previous example, let me put this in lime green. So in the previous example, both of these elements had the irreducible polynomial. Hang on, the chat window somehow preventing this from happening. Both had the irreducible polynomial, and now the pen is off. The irreducible polynomial x to the fourth minus 2 over Q. Right, so both those elements, fourth root of 2 and I times the fourth root of 2, have the irreducible polynomial x to the fourth minus 2 over the rationals. But what happens is when you extend the base field, when we make our f bigger, our sort of starting field bigger, and make it Q root 2, then that x to the fourth minus 2 factors, and the irreducible polynomial of the fourth root of 2 over Q root 2 is x squared minus root 2. But the irreducible polynomial of I times the fourth root of 2 is actually x squared plus square root of 2. and those are both over the base field Q adjoin square root of 2. So I don't know. That's like a kind of a weird example an interesting example to meditate over in your copious free time. Not going outside. Yeah, it's so again, adjoining the fourth root of 2 and I times the fourth root of 2 to the rationals, that gives you isomorphic field extensions. But adjoining those two elements to Q adjoin where you already have the square root of 2 sitting around, that actually gives you different extensions. So I don't know, wacky. 6 minutes. Let me just sort of press on. And actually, I want to just talk to everybody just for a bit. Okay, so one last thing to note, and this is actually the end of the proof of this stuff here. So we already showed that these are isomorphic if f alpha equals f beta, and now we're going to show that this next result will actually imply the converse, that if these two are isomorphic, then they actually have to be exactly the same polynomial. So the theorem says that if phi is an f isomorphism from the extension k to the extension k prime of f, and f is little f is a polynomial with coefficients in big F. Little f is an element of big F bracket x. If alpha is an element of k, and alpha is an element, and alpha is a root of, and alpha is a root of f, and phi sends alpha to alpha prime, then f of alpha prime equals 0. So that is i.e. that alpha prime is also a root of f. It's so weird that the chat window interferes with this, but there it is. Here's the proof. So suppose, oops. This is so weird, the invisible influence of the chat window, which you can't even see. So suppose little f of x equals a sub, I guess we're assuming that these things are monic, so I'll just start with x to the n. X to the n plus a sub n minus 1, x to the n minus 1, and so on, all the way down to a sub 0. And remember the point, and remember the definition of algebraic is that all these a sub i's are in the ground field. Are in the ground field, capital F. All right. So if we now apply phi to both sides, and now we also know that that if we plug in alpha, we get this, alpha to the n plus a sub n minus 1, alpha to the n minus 1, summed up through a sub 0. And now if we apply the f isomorphism phi to both sides, then we get that phi of 0 is 0, because phi is a field isomorphism. And we know that phi of alpha equals alpha prime, but also because phi is an f isomorphism, phi is an isomorphism fixing f, we know that, we know that phi of a sub I is equal to a sub I. That's because that's the definition of phi being an F isomorphism. And so then when we apply phi to both sides, we get alpha prime to the n plus a sub n minus 1 times alpha prime to the n minus 1 all the way down to, so all the alphas become alpha primes and all the a's remain the same, which means that we get exactly f of alpha prime. So there. So that again, F isomorphisms preserve the property of being a root. All right, and we'll come back to that later. Okay, everybody want to turn their mics back on? I just have a sort of very, I don't have a quick. Oh, yeah. So next time we'll pick up with a degree of a field extension, because that's actually a pretty. I think this was like. Yeah, I think that this last slide was sort of if we had extra time, and I think we don't, but this is a reasonable place to stop. So can everybody just turn their mics back on just for a sec? I just have a question about presentation. I have one question about presentation, and then sort of general, like human question. Everybody there?
Yep.
Yep.
So so we're recording this, and I realized that even though my camera is turned off, I'm making hand gestures into the air. Do you think this would be more interesting to watch if I had my camera turned on? My feelings won't be hurt if you say no. Dear God, hide your face. Or it makes no difference.
Yeah, it doesn't make a difference to me, I think.
Yeah, it doesn't make a big difference, really.
Okay. All right. Well, yeah. I guess this is the Khan Academy way to have the disembodied pen sort of talking, right? So maybe everybody's used to that. How's everybody doing? Is everybody doing okay? Since we're finishing up now. What's the weirdest thing that's happened to you over the last few days? How about that? Anyone want to share something weird that's happened? I mean, I'll share something weird that I wasn't expecting. I have to now do so many dishes. It's amazing. Like because we're cooking, the three of us are now cooking and eating at home all the time. Life is just an unending parade of dishes. It's amazing. How about you folks? Anything interesting, cheerful, crazy going on? Yeah, maybe this is the wrong time to bring that up. Anyway, so thanks very much for stopping by. So this will be posted on YouTube along with the sort of edited slides soon enough. And I'm serious. You know, see if you guys can think of something interesting to play before the show starts. I think, you know, and then just think of an interesting song to play, and if you can actually just sort of speak up and talk about why the song is sort of you find it comforting or interesting or meaningful to you, that would be great. I know, you know, things have changed, and like all of a sudden I'm all emo, but you know, I think it'll help for us to talk to a little bit to somebody else about something that's not math. I know I've really changed. Okay, everybody okay for now?
Yep.
Okay, so you take care of yourselves, and I will. I will. Oh, yeah. So remember, office hours are canceled today. My bad. But I will talk to you on Wednesday, and please drop me an email or whatever if you want to talk about some other time and or about the class or anything. And I will talk to you on Wednesday. Bye.
Bye. Thank you.
Thank you.